Okay, so let's look how interrupt processing is done on the computer and how we can transfer data in an interrupt-driven manner. So basically, if you would like to perform some I/O operation, okay, the operating system or device driver of the operating system will initiate the I/O. Okay, so the CPU is running the device driver, and assume the device driver would like to do some I/O with the device. Okay, so what do we do? The device driver initiates the I/O operation. That means it writes the command to the I/O controller register. It writes the data to be written out. Okay, or if it's a read request, it just writes the read command, indicates that it would like to perform a read operation and so on. How many bytes to be read and so on is written to the I/O controller. Okay, so assume you would like to perform an I/O operation, and device controller initiates that I/O by writing the respective registers of the I/O controller, by writing the command there. Okay, so now the hardware, the I/O controller, has the command. All right, in a bit, the bit in the I/O controller indicates, one bit there indicates whether it's a read request or write request and so on. So then the controller will do the I/O with the device. Okay, if it's a disk controller, it will instruct the head or the spinning disk to retrieve the block. Okay, it will move the head to the correct cylinder. The head will wait there until the sector comes under the head. Then finally the block will be transferred to the disk controller and so on. Okay, this is what I/O includes in a disk. If it's a serial port, for example, then the data can be written out, or here the incoming data from the serial cable can be put into the data in buffer of the input controller, serial port controller, and so on. Okay, so the I/O is done with the device by the I/O controller. How that is done depends on the device. Okay, so this will take some time. It may take a few microseconds, a few milliseconds, seconds. Okay, depending on the device here. So then finally what will happen? The data will be ready, or the operation is completed. If it's a write operation, for example, the data is written out. If it's a read operation, that means the data has come from the device and ready in the controller buffer. Okay, so during this time, what the CPU is doing? What the CPU is doing during this time? For example, during this time, the CPU can run another process. Okay, so the driver has initiated, for example, the I/O, but the driver has taken the request from an application that was running. Okay, an application may have issued a system call, read or write system call, that finally triggered the driver to initiate the I/O with the actual device. Okay, so that process that initiated the I/O may be now sleeping, will be sleeping, because that system call may be a blocking system call. So until the input output is finished, the calling process should be sleeping. Okay, so during this time, the kernel may schedule another process. So while the I/O is done, the kernel, the system may run another process in the CPU. Okay, so this will take a while. Actually, there may be several processes running. Okay, so each process may run, for example, 30 milliseconds, and context switch happen. So if the I/O takes, for example, 300 milliseconds, we can have 10 different processes running during this time in the CPU. Okay, so then what will happen? Assume that I/O operation has completed. Assume data is ready now. Okay, so then an interrupt will be sent to the CPU, indicating the availability of data, if it's a read request, of course. So then the CPU will suspend the currently running application. It may be any process that has been scheduled by the kernel earlier, right? So that process has to be suspended, has to be stopped. And the interrupt handler for that device has to be run. So that interrupt handler, now it is running in the CPU, okay? So interrupt handler will process the data. That process may include, for example, this. The data here may be taken and put into some memory location, okay? And there may be a sleeping process waiting for data, okay? So that sleeping process now may be waken up, okay? So interrupt handler will do that, will copy the data into some memory location, will process, and will return from the interrupt. And the kernel will find out which process was waiting for that data, right? So that process that was waiting for that data now can run. So its state will be changed into which state? Running or ready. It can be changed into ready state, so it may be added to the ready queue, right? So that process that was waiting for that IO to complete now is added to the ready queue, okay? So then the kernel scheduler may select one of the processes in the ready queue, or it may select the process that is suspended at this time, okay, when the interrupt arrives. A process is suspended, right? So the kernel scheduler may, for example, may choose to resume that process, or may choose another process to run in the CPU. So now that process will be run in the CPU. It may be the process that is interrupted, or it may be another process, okay? It depends on the scheduler. So this is what is happening when interrupt arrives, and this is what's happening when we do I/O with interrupts, okay? We initiate the I/O, and then we do something else, and when the interrupt arrives, we process the interrupt and so on, and we continue doing something else, or maybe we start running the application that was waiting for the data to become available and so on, okay? Is it clear? So this is how we do I/O with interrupts. So depending on the type of the interrupt, from which device it is coming, a different handler routine is run, okay? Plus, the interrupts may come from the CPU itself. We call them as exceptions. The CPU, while running an application or system code, kernel code or an application code, the code may be buggy. It may try to access an illegal memory segment. Then we can get a segmentation fault error, right? What's that? That means CPU stops the currently running application, generates an exception, okay? Raise an exception. That means now a kernel routine is run, and a kernel routine looks to a table like that, interrupt vector table. Depending on the exception number, it finds out the corresponding exception handler, all right? The address of the function that will handle that exception. For example, for a segmentation fault error, it may be a function that will handle that, okay? So we go to that entry in the table and find out the start address of the OS routine that will handle that exception. Handling that exception may be, for example, stopping the process and giving an error condition to the screen, like, for example, segmentation fault error and so on, okay? Or if the exception is page fault, that means the current running program tried to access a page that is not existing in memory, all right? Then that program is suspended, all right? Again, a special kernel routine is run that looks to that table and finds out the address of the page fault handler. So then that page fault handler routine of the kernel is run to handle the page fault. Basically, the page is tried to be retrieved from the disk. That handler routine will initiate an I/O with the disk to retrieve the page and so on, okay? So some part of that vector includes the address of the functions that are exception handlers. And some part of that table, interrupt table, includes the address of the functions that are interrupt handlers, that will handle the interrupts coming from the devices. So the first part, for example, are the exception handlers, okay? The exceptions that are generated by the CPU. Other part here, from numbers 32 up to 255, are actually for maskable interrupts. The other part of the table will contain the address of the interrupt handlers for other type of interrupts, like an interrupt from a keyboard, an interrupt from the network card, an interrupt from the disk controller, and so on. That can be a read interrupt or write interrupt, okay? So for that, we have an interrupt handler routine registered in the table so that the kernel can find out the address of that handler routine and start executing that routine whenever such an interrupt happens, okay? So we consult, the kernel always consults such a table, interrupt vector, whenever an interrupt occurs and finds out the address of the interrupt handler from that table. Any questions? So while, for example, doing input-output with interrupts, we have this problem. Assume now the data to be retrieved from the controller to the memory is not very small, not just a few bytes, but a large block, 4 kilobytes has to be retrieved. So assume the CPU is retrieving the data from the controller into memory like that. It retrieves data one word at a time. It reads one word from the controller, store it in some CPU register, and then write it to the memory. Then it retrieves another word from the controller, writes into memory. Another word is read and written into memory, okay? So the CPU just fetches the words from the controller buffer and writes them into the memory. Okay, in this way it transfers a large block, 4 kilobyte block from the disk controller to the memory. Okay, whenever a disk read interrupt happens, when the disk sends an interrupt to the CPU indicating that now a block is available, okay, in the disk controller to be retrieved into the memory. So when such an interrupt arrives, the CPU is copying the data. So while this copy operation is going on, 4 kilobyte of data is copied from the controller to the memory. The CPU is doing that, right? It actually does at least 1,000 or 2,000 move operations, executes so many move operations to copy the data from the controller to the memory. So the question is this: why do we keep CPU busy for that simple task? All right, so another chip, another circuit can be used to do that, okay? That chip is called direct memory access circuit, okay, or chip. So in this way, the CPU is relieved from that operation. The copy operation is coordinated by that other unit, okay, by that other component, DMA, and CPU can do something else, all right, during this time. Execute some application code and do some useful thing instead of just copying the data from the controller to the memory, all right? So DMA is used for that purpose. It is used to avoid programmed I/O, which means that the CPU is just copying with a simple program the data from the controller to the memory, okay? So now with DMA, CPU is not doing that. The DMA is controlling and coordinating that activity. So for that, of course, we have a special circuitry, DMA controller. In this way, the data transfer operation from the disk controller into memory bypasses the CPU. It is not going over the CPU anymore, okay? So DMA can operate in this manner. Assume, for example, the CPU, okay, an interrupt has occurred, for example, or the CPU, the process would like to, the software running in the CPU would like to transfer some amount of data from the disk controller into some buffer in memory. From disk controller to memory has to be some number of bytes, let's say 4 kilobytes, has to be transferred, okay? So now, how do we perform that transfer? The CPU, okay, the device driver running in the CPU now tells to the controller, disk controller, to transfer the amount C bytes of data, for example. C may be 4 kilobyte, okay? The driver here instructs that to transfer that much of data to some buffer here, okay? So we issue a command here like that. Please transfer that much of data to such an address, okay? So CPU just writes that command to here and then its job is finished, okay? So then the CPU can do something else. It can, for example, execute an application code, a kernel code, something else, okay? So now the disk controller and the DMA will do the transfer operation without using the CPU, okay? So the disk controller will initiate the DMA transfer. This controller will send the bytes or words to the DMA controller, which in turn will send the bytes or words to the buffer. Or the disk controller may directly send the bytes or words to the memory, depending on the architecture, with the help of the DMA. DMA, for example, can get the memory bus, inform the disk controller that the memory bus is available for the transfer now, and then the disk controller can transfer the data, 4 bytes, for example, to the memory. And this can be done repeatedly until all the data is transferred from the disk controller to the memory, okay? So during this time, while transferring 4 kilobytes of data, the CPU is not doing anything regarding that, okay? It is executing an application code. Of course, while executing something else, the CPU may also compete for the memory. It would like to retrieve something from the memory into some registers, okay? Here, DMA is also competing for the memory. It would like, for example, open the memory bus to transfer something from here to there, okay? So this is cycle stealing. Basically, DMA steals cycles of memory to access the memory from the CPU, okay? So they are actually sharing the bus, memory bus. That's okay. But the CPU can execute code in parallel with the DMA operation, right? So this is what we gain. While CPU is executing something, the DMA and this controller is actually doing the transfer. And these two activities can go in parallel, even though they share the same memory bus, okay? Any questions here? So far we have talked about hardware operation, how the hardware operates, okay? How hardware can be used to transfer data between the device controllers and the memory host, okay, vice versa. So now let's look to the application interface. The operating system is responsible to give a nice input-output interface to the applications, a set of functions, so that the application can just call those functions to do the I/O. The applications does not have to deal with the details of the hardware, okay, with the interrupts and so on. You don't want to deal with them, okay? So let's talk about that application interface here. So the operating system implements the system calls, right? And we have implemented one system call, right? So similarly, we have different system calls, 300 system calls. Some of them are I/O related. Read system call, write system call, open, close, and so on. So scanf function, for example, or printf function are library functions that are actually finally calling read and write system calls, okay? Scanf is finally calling the read, and printf is finally calling the write system call, okay? So the operating system is providing those nice system calls to the applications and to the libraries so that they don't deal with the hardware directly. So input-output subsystem of the operating system implements the system calls, I/O system calls, so that we have a set of system calls that can be used for all type of devices. So it is done by classifying the devices into different categories, like block-oriented devices, character-oriented devices, and so on. And for each type, we specify some system calls that are required. Some system calls actually can be used for all type of devices, like read-write, but some system calls make sense only for some devices, like seek system call, lseek system call, which is actually seeking to the correct position on the disk. It can be used for random access to the disk or to a file. That is actually a system call that makes sense for block-oriented devices, but not character-oriented devices, okay? For example, the keyboard should not be accessed in a random manner. It is accessed always sequentially, right? So random access does not make any sense for keyboard. So therefore, for character-oriented devices, having a system call like lseek doesn't make sense. But for block-oriented devices, such a system call is useful. And for those class of devices, the operating system provides such a system call, okay? So in order to make the application interface as simple and as nice as possible, the operating system actually classifies the devices and their behavior into some general classes. And for each class, the OS provides some set of well-defined functions, system calls, that the applications can call, okay? So in this way, the applications are just using those system calls to do I/O. You just have to know those system calls as a library implementer or application implementer, okay? Now, let's look to the operating system implementer. The operating system implementer, the operating system is huge code, right? Maybe 4 million, 10 million lines of code. So it has lots of different components. Not all components are actually dealing with the hardware directly. The operating system itself is layered. And at the bottom, we have the device drivers. That layer is responsible to deal with the hardware directly. Device drivers know how to touch the controllers, retrieve the data or write data to there, okay? The rest of the OS does not have to know. So if the rest of the operating system code would like to do I/O with some device, they just call the respective driver function. And this respective driver function, like a read driver function or write driver function, knows how to access the device registers to do the actual I/O, okay? So therefore, what we have is, at the bottom, we have a device driver layer as part of the OS that hides the differences among input-output controllers from the rest of the operating system. So the rest of the operating system does not have to deal with the details of the hardware devices, okay? They just call the I/O. Whenever they would like to do I/O with the disk, for example, the file system, whenever it would like to retrieve a block, it just calls a driver function to retrieve the block, okay? So therefore, we have some encapsulation layers of software here. Device driver hides the details of the devices from the rest of the kernel. And the rest of the kernel, the I/O system calls, provide to the applications a set of nice functions, okay, that the application can call directly to access the hardware and to do I/O, okay? So we said that the devices are categorized into generic classes. And while doing that, the features of the device are observed. So we can actually examine or investigate the devices in many dimensions, in many aspects, okay, and classify them. For example, some devices can be classified as character or stream-oriented devices or block device. Hard disk is a block device. Keyboard is a character-oriented device, okay? We can classify the classify the device as whether they are sequential access device or random access device. Hard disk is a random access device, right? You can jump to an arbitrary location and access the data directly. But keyboard is a sequential access device. Printer is also a sequential access device, right? We can classify device based on whether they are shareable or dedicated, depending on their speed of operation, and depending whether they are readable, writable, or read-only, or write-only device, okay? A printer is what? It's a write-only device, right? But a scanner is a read-only device, right? So then the system organization is something like that. Hardware and software system organization. At the bottom we have the devices, actual devices. It can be a mouse, keyboard, it can be a hard disk. And for each device we have the hardware controller, right? We have the respective controller. For the hard disk we have the device controller, hard disk controller. For the keyboard we have the keyboard controller. So these are the chips, right? And then we have the software, all right, the operating system. So at the top we have the input out, we have the system call interface to the applications. At the bottom we have the drivers that are actually dealing with the various device controllers. So for the disk device controller we have the disk driver. For the keyboard controller we have the keyboard driver. So the keyboard driver, that software, knows how to access the registers here, how to program them, how to get data from here to here, and how to write data from here to there, and so on, okay? Similarly, the floppy device driver knows how to access the floppy drive and so on, okay? So that part of the operating system is the device driver layer. So we have different device drivers here. And then we have the input-output subsystem of the operating system that is above the device driver layer. That does something else related to I/O. For example, buffering, caching, okay, error checking, and so on. So that input-output subsystem is I/O subsystem. Is again including some functions related to I/O, but those functions are not directly touching to the hardware. Okay, they are actually calling the functions of the drivers. All right. So then we have the rest of the kernel, and at the top we have the system call interface to the applications. Okay. So if you look to the devices, we have lots of different devices, and their characteristics are also very different. We can classify them in many dimensions, aspects, using many aspects. So considering their data transfer mode, how data is transferred. From the keyboard, the data is transferred character at a time, right? From the disk, the data is transferred block by block. So therefore, disk is block-oriented device. Terminal is a character-oriented device. Access method, sequential access is possible to some devices like modem, no random access, or keyboard, but CD-ROM or hard disk are random access devices. And transfer schedule. So, for example, some devices are synchronous, can be considered synchronous, some asynchronous, meaning that the next transfer is predictable in some devices. For example, for tape, or for CD-ROM, or for example, what else? For hard disk also. So you can expect when you can retrieve the next data, okay? Assume you are continuously reading the tape. When you have read the block, one block, the next block will arrive maybe 50 milliseconds later, okay? Not 5 days later. But for the keyboard, you don't know when the next byte will arrive. It depends on the user. It may arrive 5 seconds later or 5 days later, okay? So therefore, this keyboard is considered as an asynchronous, has an asynchronous transfer schedule, and tape has a synchronous transfer schedule, right? Some devices are shareable, like for example, keyboard. You can have lots of processes that are actually getting input from the same keyboard, okay? Depending on the cursor on the window, that process in that window will get the input, but you can move the cursor to another window, and that process in that window may get the input from the keyboard. So keyboard has to be shared, but the tape is usually accessed by one application at a time, okay? And the speed of the device are also very different. So in terms of latency, seek time, transfer rate, and so on. So hard disks are quite fast, but printers are very slow, keyboard is very slow, mouse is very slow, right? CD-ROM is quite fast compared to others, and so on. And I/O direction. For some devices, you can actually operate in one direction. CD-ROM can be just a read-only device, right? You just read. But graphics controller is a write-only device. You just write. Printer is a write-only device. And hard disk is a readable and writable device. So let's look to these classes a little bit more. And what kind of system calls we need to supply to the applications for each class. For block-oriented devices like hard disks, okay, or CD-ROMs, the commands that applications can issue should look like the following: read, write, and so on. Read means that we would like to get some data from the hard disk, write for something to the hard disk, okay. Seek means that we would like to access an arbitrary block on the hard disk, okay. So these are the system calls that the applications should be able to invoke. And finally, the respective device driver has to implement similar functionalities, okay. Has to have a read function that is actually touching to the disk controller and retrieving the data there. The device driver for the disk has to have a write function that is actually transferring one block from the memory into the disk controller, okay. Plus the disk driver has to have a seek function that is actually moving the head to the correct location on the disk and getting the block there and so on, okay. So we should have such functions for block-oriented devices like disk drives. Actually, disks can be also accessed in one of two modes. You can access a disk using files by opening files, writing into files, and closing them, right? That means you are accessing the disk through a file system. But you can access the disk in a raw mode as well. You just open the device and access it directly, block by block. This is also possible. You can jump to an arbitrary block, read it, write to an arbitrary block to disk, and so on. This is what you will exercise in Project 5. Okay? You will not go through the file system to access the disk. So far, you have always accessed the disks by opening files, right? You did not directly access the hard disk in blocks. Now, in Project 5, you will just directly access the disk, retrieve a block, examine what's inside there, and so on. Okay? So, of course, you can also open and map a file into your virtual address space and access the file as if you are accessing memory. So, on the other hand, with character devices, what are the functions that applications should invoke, system calls that applications should be able to call? You would like to get a character, right? So, we can have, for example, a get library function or system call, a put library function or system call. Put will put a character, for example, to the character device. It can be, for example, a serial port. Get will get a character from the character device, from the serial port, okay? So you are transferring one byte at a time or a few bytes at a time. But here, for example, you don't have to have a function like seek, okay? That doesn't make sense for character-oriented devices. Any questions? So, besides those character-oriented devices like keyboards, like terminal, screen, and like, for example, the serial port and so on, they are character-oriented devices. We have also block-oriented devices. Some other devices are falling into different category, like, for example, network cards, okay? They are not block devices. Network is not a sequence of blocks, right? A hard disk is a sequence of blocks, but network is not like that. But network is also not a character-oriented device, okay? So you are dealing actually with packets and something else and so on. So it has its own interface. It's a socket interface, so therefore the system calls that are used to do some network operations are different. There is a socket API that operating system provides to the application so that you have to use that API to open network connections and send data through these connections and receive data through these connections, okay? So it has its own API. Besides that, we have some other different devices like clocks and timers. We have a real-time clock in the computer that is keeping the current date and time, okay? So you can read, for example, even you power off your computer, okay? It keeps the current date and time. When you boot up your system, the kernel may read the current date and time from that device. Which device? From the clock device, okay? Plus, we have another device, a chip, a circuit, timer, which is called PIT, Programmable Interrupt Timer, whose job is to give periodic interrupts to the CPU, timer interrupts. Why do we use that? For example, in round-trip scheduling, we use that, right? Every 20 milliseconds, we get an interrupt and check whether the time slice has expired for the current process and so on, so that a running process will not hog the CPU resources. So having periodic interrupts given by a device is useful, okay, for various purposes. So we have such a device which is called PIT, Programmable Interval Timer. So after that interval of time has elapsed, it gives an interrupt. Again, after some time later, after the period interval has elapsed, it gives another interrupt. Okay, so that interval is programmable. Okay, you can write into one of those registers of the PIT to specify the interval after which the interrupt should be given. Okay, so therefore it's called programmable interval timer. It is used for timings periodic interrupts. All right. So now, how can you access those devices? If the application would like to access those devices, what kind of system calls make sense to provide to the applications? Reading, writing? That doesn't make much sense, right? Reading and writing data makes sense for some devices that are actually transferring, giving you some data or consuming data. The PIT is not consuming data, or the clock is not consuming data, right? So you can invent different system calls for that, okay? For example, get current time system call or something like that. Or maybe write interval to timer system call or something like that, okay? Or there is actually a system called IOCTL, okay, input-output control, IOCTL system call that's provided by various operating systems. That is used actually to implement other special commands to access such different devices. Okay, so IOCTL takes 3 arguments. One is the file descriptor corresponding to device. The second one is the command that you would like to give the device. And third one is a pointer to a memory area, which is a structure, okay, that can be used to pass information between the device and the memory, right? So with that, you can implement any command that can be given to the device, okay? You can, for example, use IOCTL to access the current time and date in the clock device. Or you can use the IOCTL to set the register, interval register of the PIT device, okay? So IOCTL is used for that purpose. It's a general purpose system call that can be used to execute various commands on the devices, okay? So that those commands are not read-like or write-like commands. Different commands are needed for the device, all right? All right, another issue is the blocking and non-blocking I/O and asynchronous I/O. So while the applications are doing I/O with the device, we have several choices. So far you have actually used only one choice, the blocking I/O. What are you doing in your application when you would like to read some data from the keyboard? Which function are you calling in your C program? Or in your C++ program, C++, right? So if you call that and if the user did not press the keyboard, what happens? Blocks, right? Did you ever use non-blocking I/O calls? No, right? So you have used blocking I/O calls where the current running process suspends until I/O is completed. In the scanf case, until the user presses something, right, and hits the return key, then the scanf returns and the program continues running with the next statement, right? So you have programmed in this manner. So it is easy to program, okay? It is easy to understand, but it is not sufficient. Assume you are doing the I/O from various sources. You are doing the I/O with the keyboard. At the same time, you would like to retrieve some packets from the network. At the same time, you would like to read something from the disk and so on. All right? So that means if you block on the keyboard, then you cannot read from other sources, right? So sometimes it's not a good idea to block forever and wait until the user presses something, which may take a while, 2 hours later, right? So during this time, maybe you would like to read some network packets and buffer them, and so on. So then what is the choice that we can have? You can use multi-thread applications, right? You can have one thread waiting for I/O from the keyboard, another thread for I/O with the network connection, another thread for I/O with the disk, and so on. Or we can use non-blocking I/O. Even though you have a single thread, you can use now non-blocking calls where now the I/O calls are not blocking. You call an I/O system call like read write, but it's not blocking. What it is doing, for example, you would like to read from the keyboard, and the user has pressed some keys and they are buffered in the kernel but not given to the application yet. When the application calls to read on the keyboard descriptor, then what will happen? Those bytes that are available will be returned immediately and read will return immediately. Okay, so read will return as much data as possible and it will return immediately. So no I/O call is blocking. If there is some data buffered, it will return that. If there is nothing buffered, it will again return with an error condition indicating that there is no data retrieved and so on. Okay, so every system call that you call is returning with as much data as possible. Okay, but it's not waiting for data to arrive. Okay, so then the application program has to be designed in a different manner. Later on, you have to go and check again whether there is some data and again. You have to invoke the read system call again. Okay, hoping this time there is a data. Okay, and if there is data in the buffer of the kernel, then you will retrieve it. Otherwise, again, the system call will not block. Right? So the programming of the application is different now. It's more difficult and so on. Okay. The third way of programming I/O in the applications is now asynchronous I/O. In the non-blocking I/O, what you do? You try to do I/O. Okay? If there is data available in the buffer, you retrieve that, but you never block. In the asynchronous I/O, you don't do that. Okay? What you do, you just initiate the I/O, and again, you are never blocking. You just initiate the I/O. Okay? You just initiate I/O, and when the I/O is completed, then the kernel informs you. In the non-blocking case, the kernel is not informs you when the I/O is completed. You are not initiating the I/O. You are just trying to do the I/O. If there is something in the buffer, kernel buffer, you retrieve that, and then you do something else, and later you again do the same thing. You invoke the system call, non-blocking system call to do the I/O. If there is something, you retrieve that. Okay? So you repeatedly call the read function in non-blocking I/O to read something. But here you call initiate the I/O, specify how many bytes you read, for example, and then you are not calling the same function again. The kernel is doing the I/O with the actual device and so on, gets the data, and then informs you, signals you. We have seen the UNIX signals, for example, right? It sends a notification to the application in an asynchronous manner, why it's called asynchronous, okay? Then you might have registered a function to handle that notification. That function of your application is called in an asynchronous manner to do the I/O, to get the data from the kernel buffer and do something, whatever necessary, all right? So this is how asynchronous I/O is working. Of course, it is difficult to use now because the signals or notifications may arrive to you, to your application from the kernel at an arbitrary time. You have to design your application to operate in an asynchronous manner. You have to, in your application, you will include some handler routines, notification handlers, signal handlers, that will be called whenever the I/O operation is completed, okay? Of course, now those handlers will be started running at any time during the execution of your process, okay? So they may be source of race conditions and so on. So asynchronous I/O is difficult to use. I/O subsystem of the kernel will signal the process when input output is completed. So this diagram illustrates these two methods, the asynchronous I/O and blocking I/O, synchronous I/O. Blocking I/O is also called synchronous I/O. In blocking I/O, the requesting process invokes the system call and is blocked. The device driver initiates the I/O with the hardware. The hardware is doing the actual I/O. Data is transferred to the kernel buffers, and finally, it is given to the application, and application is started. It can consume the data now. Okay. During this time, the application is just waiting until the I/O operation is finished. When the application is started again, that means the data that the application is waiting is ready. All right, scanf has returned, you have the data in your variable, and so on, okay? This is synchronous I/O or blocking I/O. In asynchronous I/O, the application is just initiates the I/O with a system call, all right? And the application goes and does something else. It is maybe executing another function, doing some other job, and so on, okay? During this time, the hardware is doing the actual I/O, and application is executing in the CPU, running another function, for example. And when the I/O is completed by the hardware, interrupt is given, and interrupt handler transfers the data to the kernel buffers and so on. So now the kernel notifies the application. This notification is what? It asynchronously runs a registered handler function of the application. Okay, that handler function of the application is now processing the data available. Okay, so that handler function of the application is run in an asynchronous manner whenever data becomes available at that time. Okay, so this is asynchronous I/O. Any questions? So now we will talk about the rest of the kernel input-output subsystem. Okay, we have talked about how the device drivers can access the controllers to retrieve data, to write data, access the registers, and so on. That was the part related to the device driver writer. So device drivers are the bottom layer of the input-output subsystem of the kernel. We have the other layer, okay, the rest of the input-output subsystem of the kernel, which is doing again some input-output related tasks. All right, so we will talk about them now, like buffering, scheduling, caching, and like error checking, and so on. In the next lecture, we will talk about those issues, the functionalities that are implemented in the rest of the kernel input-output subsystem. Okay, any questions? All right, we can stop here.